All right, let's look at some optimization problems. Optimization are a very nice application of calculus because it's looking at how we can make something as big or as small as possible. And so that idea of local max and local min, or even global max and global min, that's the idea of optimization problems. So let's think about the state of Colorado. Colorado is essentially a square, or rectangle rather. Here's the state of Colorado. And if we wanted to optimize the altitude of Colorado, that means find altitude. That means find where Colorado is both the biggest height and the smallest height. And for Colorado, it happens that the highest point is a local max. Where? I'm not sure exactly on this map, but the highest point, let's just say that it's right here, would be a mountaintop, a local max. The lowest point is not a local min. So the lowest point isn't one of those cases where it's getting less and less altitude in this direction. Rather, the lowest point, it just kind of gets lower and lower and lower and lower and lower as we head out toward the plains. For those of you not familiar with uh, American Midwestern topography, this is a very mountainous area, and then it gets very flat. And so it just gets flatter and flatter and flatter, and we reach, as we head out, we go toward our lowest point, which isn't a local min, it's a global min, which means that it happens on the border. Okay, so what's the distinction between local and global extrema? Well, local extrema happens when my partial derivatives equals 0, and in some local region, it is the biggest or smallest value. Whereas the global extrema, the definition for a global extrema is that a global maximum occurs when there is some point that is bigger than all other points in a given region. And that will either happen at a local max value or at an endpoint. And the global minimum says that there's some point that's smaller than all other points on some given region. So in these optimization problems, the task is to find the global max or min. And we're going to be looking at two different types of problems. The first type of problem is called a constrained optimization problem, when there are boundaries that we need to consider. And the second case that we're going to be looking at is called an unconstrained optimization, where there are no boundaries. So we can look at all values. So let's jump into a problem. So for the first case, for the unconstrained optimization problem, the first thing you do is find the critical points, and then we're going to investigate whether the critical points give global max or min. So let's think about this example. It's an economics example where we're trying to maximize the profit and minimize the cost. And so we know that profit equals the amount of money we bring in minus the amount of money that we spend. And the amount of money we bring in, which is called revenue, is the price at which we sell something times the quantity that we sell, PQ. So let's say that we are manufacturing two items and they're sold in two separate markets. So Q1 and Q2, those are the quantities that are demanded by the consumers for the different prices, P1 and P2. Okay, so that we're given an equation for that relates my price of object one and the quantity that is demanded. So as price goes up, the quantity demanded will go down. And here's price of 2, how it relates to the quantity sold. And then we're given an equation that finds the company's total production cost. So it depends on how much we're producing of each different item. And what we want to do now is we want to take our total cost and then our prices and maximize total profit and figure out how much of each product should be produced and then what would be that maximum profit. Well, we know that profit equals revenue minus cost. Well, my revenue is price times quantity. So for my first item, my price is 600 minus 0.3 Q1. That's the price times the quantity plus price 2 times quantity 2. So that's my total profit. I'm sorry, that's my total revenue. Right here is my revenue. And then I'm going to subtract that from my cost. So then I get this profit equation. Profit equals, well, distributing everything, we're going to get 600 Q1 minus 0.3 Q1 squared. So I'll just finish writing this out. So we get this equation here. And this equation tells us our profit as a function of quantity of item 1 and quantity of item 2 sold. Well, what we need to do in order to figure out the maximum profit is find the partial derivative. So the partial derivative of profit as we change Q1. Well, going through, we're going to get 600 minus 0.6 Q1 minus 1.2. And then over here, minus 0.2 Q2. And we want to see when this equals 0. And we want to get the partial derivative with respect to Q2. So that's going to be 500 minus 0.4 Q2 minus 1.5 and then minus 0.2 Q1. That's the partial derivative of this with respect to Q2. And this we need to set equal to 0. All right, well, so now what we have done is we've took our equation, we took our profit equation, we expressed our profit equation in terms of Q1 and Q2. That's the quantity of items 1 and 2 sold. We took their partial derivatives and we set them equal to 0, because when the partial derivatives equal 0, that's where you're going to have a local max or min. So I'm going to jump to the next page where we have the solution written out. This is the equation that we just generated. And notice it's a system of 2 equations, my 2 variables Q1 and Q2. So we can go through using linear combination or substitution to get my values of Q1 and Q2 that satisfy this system. And that's just algebra 1. And so given these values of Q1 and Q2, we can find the price values because, going back a page, we know that the prices depend on Q1 and Q2. So if we just plug the value of Q2 in there and Q1 in there, we'll get the prices that we should set. That's the price in which we should sell something to either max or minimize it, depending on what we'll find. So these are my given prices. . So, and then what we want to do is we want to say, well, let's be sure whether that's a max or a min. Let's be positive whether or not these prices, which correspond to these quantities sold, which correspond to my partial derivatives equaling 0, how can we be sure that that maximizes my profit and doesn't minimize it? Well, if we remember from the last video, what we can do is look at the second derivatives. So let's look at the derivative of profit, second derivative of Q1, Q1. So that is going to equal negative 0.6. And the partial of Q1, Q2 is negative 0.2. And the partial of Q2, Q2 is negative 0.4. And what we do is we say, okay, well, D equals negative 0.6 times negative 0.4 minus negative 0.2 squared. And this value is greater than 0. So the fact that it's greater than 0 implies that it's going to be a max or a min. And the fact that these values here are negative mean that it's going to be a maximum value. Because remember, if these values are negative and the D value is positive, we're talking about a maximum. So that proved that these prices selling this many items will maximize my profits. So this is a very good economics application of optimization problems because it takes our revenue equation and our cost equation and it figures out what is the best price for us to sell something. Let's look at another example. So we've got a delivery truck system. So the idea is this: a delivery of 480 cubic meters of gravel needs to be made. So this is how many cubic meters we need. And there's a trucker who is going to purchase an open top box in which to transport the gravel in numerous trips. So gravel is going to go in here. Gravel, gravel, gravel. The total cost to the trucker is the cost of the box, so how much you have to pay for the box, plus $80 per trip. So every time the trucker makes a trip, he has to spend or she has to spend $80. The box must have a height of 2 meters. So that's a requirement for packing the gravel. So this must be 2 meters. But the trucker can choose the length and width. Okay, so the cost of the box is $100 per meter squared for the ends. So here are my ends. 50 meters squared for the sides. And for the bottom of it, where it needs to be the most durable, we're spending $200 per meter squared. Okay, so the idea being smaller box is cheaper, but it's going to require more trips. So we need to figure out what will be the ideal box size so that we make few trips, but also so that we don't spend that much to build our box. All right, well, we have all the expenses right here, but let's think about it. Our end has we have two end pieces here and here, and our end has the dimensions of 2y, and there are two of them, and that gives me the total area of my end. And I know that for my ends, I am spending $100 per meter squared. So the total amount that I'm spending there is going to be 400 times y. And for my sides, well, for my sides, the dimensions are x by 2, so 2x, and I have two of them, and I'm spending $50 per meter. So I'm going to spend $100 times x for my sides. And the bottom, there's only one bottom because it's an open top. So my bottom is x, y, and I'm spending $200 for that. So 200 x, y. So those are the costs of my box. Well, what about the cost of the trip? The dimensions of my box, or the volume of my box rather, is 2xy. So if I take the total amount of gravel that I need and divide it by the volume that I have, this is going to equal the number of trips. And if I multiply that by $80 per trip, this is going to give me how much money I have to spend on the trips. Well, this ends up equaling 240 over xy times 80. Okay, so these are all of my expenses. The cost for the end, the cost for the sides, the cost for the bottom, and the cost for the number of trips. So the total cost that I'm spending is the sum of all those. So the cost equals 400y plus 100x plus 200xy plus 19,200 times xy to the negative 1. Okay, so now what we're going to do, since that is our cost function and we want to minimize this, we're going to find the derivative. So the partial derivative with respect to x, we have 100 plus 200y minus 19,200 times, or rather not times, but divided by yx squared. And the partial derivative with respect to y, we have 400 plus 200x minus 19,200 over x y squared. Okay, well now we're just going to get into some algebra. So first things first, this is going to be a local min when these equal 0. And what I can do is I can get rid of, I can divide each of these terms by 0. So we get, setting this up, we're going to get 1 plus 2y minus 19.2 over y x squared equals 0. Or rather, we could set it up like that. That's this equation here. And then 4 plus 2x equals 19.2 over x y squared. Well, this looks pretty challenging to to solve. But if we just divide both of these equations, we'll get 1 plus 2y over 2 plus x equals xy squared over y x squared. Well, the x's we'll have a little simplifying here. That goes away. Let's use a highlighter. That's going to go away. That goes away. That goes away, and this goes away. Just realized I made a small mistake up here. This should have been 200x, not 100, which makes this 200 and makes this 200 and makes this a 2, which makes this 2. Yeah. Good. Okay, so that's going to cause, now the 2's cancel out. And if we cross multiply, we're going to get 1 plus y x equals 2 plus x y. And let's do this on the next page so that we have a little bit of room. So continuing to solve this, we get x plus xy equals 2y plus xy, and these cancel off, and so we get left with the relationship that x equals 2y. Well, that's going to be helpful for us. So we can take this relationship that x must be 2y, which we got from setting, going back a page, which we got from setting the partial derivatives equal to 0 and then solving. So when we set the partial derivatives equal to 0 and solve them, we got this relationship that x equals 2y. Well, now let's put this relationship back into my partial derivative with respect to y. So the fact that x equals 2y, we can put there and there. And we get that the partial with respect to y. And let's divide every term by 100. So we get 4 plus 2 times 2y minus 19.2 over 2y times y squared equals 0. And if I keep going with this algebra, let's move this term over and then multiply. And what we'll get is 8y cubed plus 8y to the fourth minus 19.2 equals 0. Okay, so correcting a small mistake, this is not 19.2, but just 192. And now we could divide an 8 out, and we get y cubed, or sorry, y to the fourth minus y cubed minus, that's a plus 24 equals 0. And at this point, we could use a calculator to get this or do a little bit of other work, but we get that y equals the solution to this problem, and you could use your calculator, is that y equals 2. And therefore, x must equal 4. Okay, now that we have the solution to what is either the max or the min, we need to prove, is it a max or is it a min? Well, to save a bunch of time in algebra, here's our solution. So um, we have our partial derivatives, which we set equal to 0, found out that 2y equals x. Here's the work that we did to solve that equation, and we found out that our max min point would be at 4, 2. And then to determine whether it's a max or a min, we need to look at the second derivatives. So our second derivative with respect to x is going to be 96 times 2 over x cubed y. And my second derivative with respect to y, using this, is also going to be 96 times 2 over y cubed x. So just taking partial derivatives here. And f partial xy will equal, well, that's going to equal 96 over x squared y squared plus 1. Now what we do is we look at the d value. So we're looking at the d value, the discriminant, at the point 4, 2. And when we plug in the d value into there, sorry, when we plug in 4, 2 into our equation for the discriminant, we get a positive number. And we notice that both of my partial xx and partial yy, both of these values are positive. So the fact that both of those values are positive, we know that it's going to be a min. Okay, so looking at how we can determine whether a function has a global max or minimum when we're talking about some function being on a given region. So let's think about this function here, and it's on the disk x squared plus y squared must be less than or equal to 1. So we know that our partial derivative is 2x and 2y, and these will be 0 at the point 0, 0. So with just a little bit of intuition, we know that this is going to be a minimum, because as x and y get bigger and bigger and bigger, up until the point when x squared plus y squared must be less than or equal to 1. So we're talking about this region here. So our smallest value is going to occur right here. And our maximum value is going to occur on the edge. So our minimum value at 0, 0, our minimum is going to be 1. Plugging 1 in for that. And our maximum is going to be when x squared plus y squared equals 1. So plugging 1 in for that, our maximum value will occur, or our maximum value is 1 plus 1, which is 2, and it occurs anywhere where x squared plus y squared equals 1. Well, what about this point here? It extends on the xy plane. First derivative, or partial derivative with respect to x, is as follows. This is going to have a minimum when, or this equals 0 when x equals 1. My second partial f partial y equals 2y minus 4. This equals 0 when y equals 2. So at the point 1, 2, I'm going to have a local max or min. Well, what we can recognize is that since we're looking at the whole xy plane, x and y can get as big as possible. And since our highest degree is squared, and it's plus y squared and plus x squared, as x and y get huge, this will grow for forever. So there's no maximum. So therefore, this value must be a minimum. So our minimum value would be f of 1 comma 2. And then we could just plug that in. So this is just reiterating what we just looked at before. Okay, some definitions that we need to be familiar with. First, a closed region is one which has a boundary. So a closed region, for example, was that problem earlier, which was that x squared plus y squared must be less than or equal to 1. That's an example of a closed region. A bounded region sorry, let me restart here. Restart. I was just talking about a bounded region. A bounded region is one that doesn't stretch to infinity. So a bounded region, an example of that is x squared plus y squared less than or equal to 1. That's an example of a bounded region because you're only looking in one little area. The closed region, which I incorrectly described a second ago, a closed region is one which contains its boundary. So, for example, here my bounded region was x squared plus y squared must be less than or equal to 1. This is also closed because it equals my boundary, which is this boundary point. So, for example, we've got here a square, and x can be less than or equal to negative and positive 1, y can be less than or equal to negative positive 1. So this is both closed and bounded. It's bounded because we're talking about everything in here, and it's closed because it includes my boundary. The first quadrant, so in this problem, we're talking about x must be greater than or equal to 0, and y must be greater than or equal to 0. So everything in here. This is closed because it includes my boundary, but it's not bounded because it can go on forever in that direction. Here we have the disk x squared plus y squared is less than 1, so it's bounded because there's a boundary, but it's not closed because it doesn't include my boundary. You get the idea. Well, the reason why we're talking about this is because it opens up an important theorem, which is called the extreme value theorem. It says if f is continuous function on a closed and bounded region, then f has a global maximum at some point and a global minimum at some point. So for example, does the function f have a global maximum or minimum on the region defined by this? Well, notice that while this is, let's see, you've got closed and bounded. Is it bounded? Yes. Is it closed? No, because it doesn't include 0. So because it doesn't meet this criteria, there's no global max or min. So let's look at a picture of what that graph looks like. This is going to go on forever and ever and ever, having a vertical asymptote there. So because it doesn't contain our boundary point 0, 0, 0, or sorry, just 0, 0, it will not fall into our extreme value theorem. Okay, so looking at, let's think about, what some example problems might look like. If we want to estimate position and an approximate value of the global max and global min, what we can do is we can say, well, all right, global max and global mins will probably occur at these peaks. So here we have 4, 5, 6, 7. So this has a value there of 7. And here we have 2, 1, 0. This has a value of -1. And this here has a value of 11. So my global maximum is 11, and my global minimum is -1. And what are the positions? So my global max is occurring at roughly, let's say 1, 2, 3, 4, 5, roughly 5, 5. And my global min is occurring at about 1, 4, 0.14. So let's look at one of these examples. We have this following function on this region. So we know that looking at the partial derivatives, we're going to have a local max or a local min at the point 0, 0. And we know that because of this shape that that's going to be a local min. What about the local max? Sorry, not a local min, but a global min. The global max, therefore, must occur on the boundary. So the global max is going to occur, if we think about this going on, what's going to be our furthest, what's going to maximize x squared plus y squared is this point right there, or this point, or this point, or this point. Any of those values are going to maximize the value of x squared plus y squared, because they're the, if we think about the circle that captures them, that's the biggest circle that we can put around it. So the global max is going to occur either 1, well, let's say plus or minus 1, plus or minus 1, which will equal 2. All right, we'll finish with one more problem. Actually, let's do this. I think that was enough examples. So let's just stop here, have you write down some notes about what you just learned, and you can start the problems, the corresponding problems shortly thereafter. In the next lesson, we're going to learn a much more smooth and efficient way called using the Lagrangian formula to find local max and min. So this was just kind of a rough introduction to the idea of max and mins.